Hello everyone, I am Sulekha Sharma and welcome to Sulekha Physics classes. It is the most easiest way to learn all the concept of physics through this class. Today I am coming with one more topic of this chapter, wave optics, that is Young's double slit experiment. Young's was the first scientist who explained experimentally interference pattern on the screen. Actually, previously Huygens just proposed wave theory of light, but how two waves superimpose and produce maxima and minima on the screen, that was experimentally explained by Young's double slit experiment. So, before starting this experiment, you must know about coherent source, which we already discussed in the last class. Coherent sources are those sources which have same frequency and constant phase difference between them. Why this coherent source is needed? To produce sustained interference or static interference on the screen, so that we can observe interference pattern very easily. If the source is not coherent, then in that case we get dynamic interference. It means maxima and minima are not always same at the same point, always changing with time. So it's very difficult to observe dynamic interference pattern. So to produce sustained interference, you can say static interference, we need coherent source. But you also know that this emission of light is atomic phenomena, which is very random and rapid. So it's not possible to two independent sources be coherent, because there is not a constant phase difference between the two independent sources. Then how we produce two independent sources? We already discussed about two methods, that is by division of wavefront and by division of amplitude we produce coherent source. So Young was the first scientist who produced coherent source by division of wavefront and produce sustained interference pattern on the screen. So let us start this Young's double slit experiment. His setup is, suppose here one slit is here and this slit is illuminated by monochromatic source of light. Monochromatic means single wavelength, single color light, sodium lamp. Okay. In this experiment, we always consider monochromatic source of light. Otherwise, again, we are not able to observe sustained interference pattern on the screen. So this source is illuminated by this monochromatic source of light, and again, according to Huygens principle, like this one. Okay, wavefront is there, the waves moves forward in the form of this wavefront. Again, we take two slits in front of this wavefront. When this wavefront reaches at these 2 points, again, suppose this wavefront like this one, some part is reaches here at this S1 and some part is reaches here at S2. Again, according to Huygens principle, each point on these sources acts as a source of secondary wave. So again, secondary wavelets, it produces secondary wavelets. Again, this source S2 also produce secondary wavelets, and in this way there is a screen here. These two wavelets produces interference pattern on the screen. So these are the setup. I am going to draw very neat and clean diagram here. Here the two sources are coherent sources. Why? Because these two sources are produced from the same source S by division of wavefront. Okay, so these two sources are in a position to produce sustained interference, right? Okay, so let us start this Young's double slit experiment. Okay, now this is experimental setup of Young's double slit experiment. This slit S is illuminated by a monochromatic source of light of wavelength, suppose lambda. Okay, why we take monochromatic source? To produce sustained interference so that it is easy to observe on the screen, right? And again, according to Huygens principles, if you apply wave theory of light, these are different wavefronts. Suppose after time 3, the wavefront reaches at this point. So these 2 points S1 and S2 are at the same distance from S, right? and they are vibrating in the same phase. So these two sources S1 and S2 must have constant phase difference between them because they are obtained from the same source S. So these two sources S1 and S2 acts as coherent source, right? Coherent source of light, and these two sources are in a position to produce interference pattern on the screen. Suppose here on the screen at point P, these two sources, rays from this S1 and S2 reaches at this point P and superimpose and produce interference pattern, right? So what are different conditions to produce interference pattern on the screen? At point P, whether constructive interference is there, destructive interference there. Young's explained all these things experimentally. So to calculate conditions for constructive and destructive interference, let us assume something. First, these two sources S1 and S2 must be coherent source and monochromatic coherent source and also monochromatic. These two sources have same color, same wavelength lambda. Again, let us suppose that the distance between these two sources S1 and S2 is small d. Small d is distance between two sources. And again, screen is placed at a distance capital D from the source. Capital D is distance of a screen from source, right? Again, one more assumption is there. This D is very greater than this small d. It means source and screen, source is at very large distance from the screen. Here assumption is that this D is very greater than a small d. So two important assumption: the source must be monochromatic, must have same wavelength lambda, and another one is the distance of the screen from the source is very larger than the separation between the two sources. Okay, now suppose this one is the midpoint of this source S1 and S2 D. So from this midpoint of these two sources S1 and S2, draw one perpendicular line which reaches on the screen at point O. This O is the midpoint of the screen also. Again, suppose from S1 draw one perpendicular on the screen at point A, and again from S2 also draw one perpendicular on the screen at point B. Now to calculate the interference pattern, to calculate the path difference, phase difference, you just, why this interference pattern? Due to the path difference, phase difference. And what is the path difference between these two sources S1 and S2? S1 takes this path and reaches at point P, S1P, and S2 from this point S2P. So here it's clearly from the figure that there is a path difference between S1P and S2P, and due to this path difference, phase difference is also there. You know the relation between path difference and phase difference. Okay, phase difference is what? 2 pi by lambda into path difference. So what is that path difference? Our main aim is to calculate that path difference, okay, and from that path difference we derive conditions for maxima and minima intensity, right? Okay, again it's very clear from the figure here that at O, distance from S1 and S2 is same, S1O and S2O. S1O is equal to S2O. At the center of the screen from the source S1 and S2 distance is same. It means what? Path difference is 0. Let us denote that path difference is delta x. Path difference is 0, and path difference 0 means at the center of the screen, at the center of the screen, maximum intensity. Maximum intensity. We already derived that one. If path difference is 0, It means at that point maximum intensity is there, and maximum intensity means bright fringe, right? Bright fringe is formed at the center of the screen. Okay. So at point O, bright fringe is there. Suppose the two waves superimpose at this point P, and let us take the distance from the center of the screen to this point P is x. It means at a distance x, what is formed at point P, whether dark fringe or bright fringe, maximum or minimum. So to calculate that one, at point P, what is the path difference from these two sources, S1 and S2? This one is S1P and this one is S2P, and this S2P is greater than this S1P. So path difference between the two sources is what? Path difference is, it means delta X is S2P minus S1P. Suppose if you draw one perpendicular from this one, right? This one is the perpendicular. So after this point M, both these paths are same. So this S2M is the path difference. S2P minus S1P is S2M delta X. Now our main aim is to calculate this path difference. Okay. So to calculate this one S2P minus S1P, let us first consider this triangle S1AP, right? This is normal, right? So from triangle S1P, what is this one? This is hypotenuse. So S1P square equal to this S1A square plus this OA square. Now what is this S1A? S1A is capital D. So this one is D square plus OA is what? This OA, this, sorry, not OA, this is P, na? P point, so PA, right? This PA is what? OP minus OA, and OP is what? X, and OA is D by 2. So this one is X minus D by 2 whole square. This one is S1P whole square. In the same way, you can calculate S2P by taking triangle this one, S2BP. So from triangle S2BP, this S2P square is what? S2B square plus BP. S2B whole square plus BP whole square. What is S2B? S2B is capital D. So again this one is D square plus what is BP? BP means this BO plus OP. And what is this BO? D by 2, and OP is X. So this becomes X plus D by 2 whole square. Now you get here S1P square, and here is S2P square, right? We want S2P minus S1P. So just subtract these two equations. This one S2P, okay, S2P square minus S1P square. If you subtract these two equations from this right hand side also subtracted, D square plus X plus D by 2 whole square plus, sorry, minus this one, minus D square minus X minus D by 2 whole square. This D square cancel each other, okay, and then again you just open this one, X plus D by 2 whole square. A plus B whole square means A square plus B square plus 2AB. So this one is X square plus D square by 4 plus 2X D by 2. It means 2X D by 2 to cancel. Again minus this A minus B whole square. A square plus B square minus 2AB, right? So inside the bracket X square plus D square by 4 minus 2X D by 2, right? Cancel this one. When you open this one, this X square minus X square, these two term gets cancelled, right? d square by 4 is minus, here plus, this is also cancelled. This one is xd, and again minus minus plus is xd. So you get what? xd plus xd, it means 2xd. Okay, and here again s2p whole square minus s1p whole square. So a square minus b square is a minus b, a plus b. So you can write in place of this one s2p minus s1p and s2p plus s1p. One more thing, suppose this point P lies very close to O. Suppose P lies very close to O. It means this distance x is very small. If this point P lies very close to this point O, it means S1O and S2O. If this distance is also very small in comparison to this D, so this S1P and S2P both are equal to this distance capital D. So in this case, this S1P is equal to S2P equal to capital D, right? So here S2P, we get S2P minus S1P, S2P plus S1P both are equal to D, so you get 2D equal to 2x small d. This 2 cancel, we get S2P minus S1P equal to x small d by capital D. We get the path difference at point P between the two sources is this one. S2P minus S1P equal to xd by capital D. This is the path difference between these two sources at point P. Now due to this path difference, phase difference is there and interference pattern is obtained on the screen. But at point P, due to this path difference, whether constructive interference takes place or destructive, what is the nature of interference pattern? Let us observe that one. You must know the condition for constructive and destructive. In the last class we discussed, we applied that one and we get conditions whether at point P constructive interference takes place or destructive interference takes place. Okay, so note down this one first. So hope you have noted all these things. Okay, I am going to rub it, right? You must remember path difference between the two sources at point P. This path difference is S2P minus S1P equal to a small x small d by capital D. Using this path difference, I am going to derive conditions for constructive and destructive interference. Okay. So you must remember the path difference between these two sources, that is S2P minus S1P equal to what? X small d by capital D. This x is the distance of center of the screen O to point P where we are going to find the condition, right? And this small d is distance between two sources and capital D is distance between source and screen. Now first, position of bright fringe. Position of bright fringes, right? Bright fringes means maximum intensity. In this case, constructive interference takes place. What type of interference? Bright fringe means maximum intensity constructive interference. And you know that in the last class we discussed what is the condition for constructive interference. Path difference must be, this delta x must be n lambda, na? We already derived this equation, right? Path difference is equal to n lambda. You can write even multiple of lambda by 2. And here you get the path difference, what? Small x small d by capital D equal to n lambda. So from here you get x equal to n lambda capital D by small d. Actually this is the position of this bright fringe, right? At point P, when bright fringe is formed, when distance from the center of the screen to that point x is equal to n lambda capital D by small d, where n equal to 0, 1, 2, 3, dash, dash, dash. If x is 0, it means at this point, center of the screen, bright fringe is formed. This is maxi central fringe. When n is 1, it means first bright fringe, lambda capital D by small d. When n is 2, like this one. When n is 1, first bright fringe we formed. Okay. When n is 2, second bright fringe is formed, and first bright fringe is formed at distance what? X1 is what? N is 1, so lambda capital D by small d. X2 is what? When n is 2, 2 lambda capital D by small d. Okay, this is the distance from the center of the screen to the point where first fringe is formed, second fringe is formed. In this way, this is the position of nth bright fringe, x hat equal to n lambda capital D by small d. You must remember this formula. It's very, very important. This is position for bright fringe or constructive interference takes place at this position here. N is equal to 0, 1, 2, dash, dash, dash. Right? Okay. After this, position of dark fringe. Okay. Here I am going to write position of dark fringes. Okay. So, for dark fringe, what is the condition? Okay. So, for position of dark fringe means destructive interference, minimum intensity, destructive interference. And when it takes place, what is the condition for that one? When minimum intensity is formed at point P, that path difference is delta x is odd multiple of lambda by 2. Right now, and what is path difference here between the two sources as point P? We get x small d by capital D equal to twice n minus 1 lambda by 2. So from here, this is x equal to 2n minus 1 lambda capital D comes here by 2d. Right? This is the condition for dark fringes where n is equal to 1, 2, 3, like in this way, because at the center when n is 0, we already know that from S1 and S2 at the center path difference is 0. S1O and S2O are same. So at the center always bright fringe is formed. Now first bright fringe is formed at this point n equal to 1. This second bright fringe at n equal to 2, and first dark fringe is formed at n equal to 1. It means for first dark fringe, n is 1. It means x1 is equal to, n is 1 means this 2 minus 1, 1 lambda capital D by 2d. Right? In the same way, second dark fringe, it means n equal to 2. This x2 is when 3 by 2 lambda capital D by small d. It means first dark fringe is formed at this point, lambda capital D by twice d. It means between the two bright fringe, first dark fringe is formed, right? Because first bright fringe distance is lambda capital D by small d. Here first dark fringe is lambda capital D by twice d. It means between this one, first dark fringe is formed. Between the two bright fringe, dark fringe is formed. In this way, position for nth dark fringe, you can write xn equal to twice n minus 1 lambda capital D by twice d. This is the position for dark fringes and this is the position for bright fringes. Okay, how this fringe pattern obtained on the screen? Okay, let us try to draw that one, right? Okay, now let us try to draw fringe pattern on the screen. Suppose this is a screen and what type of fringe pattern is formed. Now, okay, first you write condition for bright fringe. What is condition for bright fringe? We know xn equal to n lambda capital D by small d. And for dark fringe, what is the condition? Xn equal to twice n minus 1 lambda capital D by 2d. These are the positions for bright and dark fringes on the screen. Now let us try to draw this pattern here on the screen. Suppose this is the screen, this is center, it means this is center O, right? Now at the center of the screen, what happens? Distance from this source S1 and S2 are same, path difference is 0, it means at the center maxima is formed. Again, both sides from this center, this equidistant, right? This one. Suppose at this point, this is when n is 1, first bright fringe is formed. N is 1 means lambda capital D by small d. So here, okay, you can write here that central bright fringe, here is first bright fringe. At a distance what? This distance is lambda capital D by small d. Again, second bright fringe is formed, twice lambda capital D by small d. Suppose this one. This is second bright fringe. Twice lambda capital D by small d. Okay. And this n may be positive, negative both. On the both sides of this center of the screen, fringes are formed. Okay. Now position for first dark fringe. When n is 1, it means what? Lambda capital D by twice d. And lambda capital D by twice d is between these two, na? This distance is lambda capital D by small d. So lambda capital D by small d is this one. Here dark fringe is formed first. This distance is lambda capital D by twice d. Again, second dark fringe is when n is 2. 2 is a 4, 4 minus 1, 3. 3 by 2 lambda capital D by small d. And that is in between this one, lambda capital D by small d and this one, two bright fringes. So here second dark fringe is formed at a distance 3 lambda capital D by small d. In this way on both sides of the screen, here also first dark, here second dark, then this one is first bright, then second bright. In this way fringes are formed. Here pattern is like this one. Okay, this one is maximum. Suppose maxima is there, like this one. Again here is maxima and this is the position, like this one. Here again maxima, so this is like this one. Here again maxima, so like this one. Here is again minima, so like this one. Here is maxima. These are the position for maxima. In this way intensity pattern is formed on the screen. You can draw in this way also, like this one. This is center O, right? Intensity is formed like this one on the screen, right? This is central bright fringe. This one is first bright fringe. This one is second bright fringe. Here this one is first bright fringe on left side below the screen. This one is second bright fringe. This one is position for first dark fringe. This one is second. In this way, this one is first, D2. So on both sides of the screen, bright and dark fringes are formed, right? This is intensity distribution pattern for this Newton's double slit experiment. This one is intensity distribution pattern for interference. Here you observe that between the two bright fringes, one dark fringe is formed and all the bright fringes are of equal spacing and all the dark fringes are of also equal spacing. Distance between two dark fringe or two bright fringe, you can say consecutive bright fringe or consecutive dark fringes is called fringe width. So next topic in this experiment is, what do you mean by fringe width, right? Fringe width. Fringe width. It is denoted by, I will take this beta. This is fringe width, and this is distance between two consecutive bright or dark fringes. Distance between two consecutive bright or dark fringes. So how you derive this fringe width? You take the position of two dark fringe and take difference between that one, or either you take position of two bright fringe and take difference between that one. So let us suppose I am going to derive fringe width for bright fringe first. Okay, for bright fringe, what is, okay, for bright fringe. For bright fringe, what is the nth bright fringe position? N lambda capital D by small d, and next n to n plus 1th bright fringe. So x n plus 1th bright fringe, this one is formed at n plus 1 lambda capital D by small d, and the difference between two positions of these two positions of bright fringe is fringe width. So you can calculate in this way fringe width. First you note down that one beta fast. Okay. So now this difference between these two is fringe width beta. So this beta for dark fringe is equal to this x n plus 1 minus xn, right? And you take the difference of these two, you get this one is n plus 1 lambda capital D by small d minus xn is what? Xn is n lambda capital D by small d. You take the difference between these two, you get n and cancel, you get expression for lambda capital D by small d. This is the fringe width for what? Bright fringes. For bright fringes. It means the separation between the two bright fringes is lambda capital D by small d. And you find here that it is independent on n. Independent on n. It means the distance between any two bright fringe is always same. Fringe width is always same for any bright fringes. In the same way, you can calculate for dark fringe also. For dark fringe also, what is the condition for this dark fringe? Xn is equal to twice n minus 1 lambda capital D by twice d. And after this xn plus 1th fringe, twice in place of n you write n plus 1 minus 1, okay, lambda capital D by small d, twice d. And this fringe width for dark fringe is difference between these two, xn plus 1 minus xn. When you calculate this one, again you get the same expression. You just calculate by yourself. This minus this, these two cancel, twice n, this term twice n. Again you get lambda capital D by small d. It means the distance between two dark fringe is always, it is independent on n. So distance between any two dark fringe is always same, lambda capital D by small d. So all bright and dark fringes are of equal spacing. That's why I draw the pattern like this one. Na? Okay. Let me again draw. Okay, beta. This one, this one, this one. This is bright, this is bright, this is the bright fringe is beta. Again, this is bright, this is bright, this is beta. This one is dark, this one is dark, this one is beta. And distance between any two bright fringe or any two dark fringes is always same. All bright and dark fringes are of equal spacing. Okay, so this is the expression for bright, this fringe width. In case of dark and bright both, expression is lambda capital D by small d. This formula is very important from numerical point of view. In numericals, questions comes from this fringe width, okay, formula based on this one, beta equal to lambda capital D by small d. Okay, one more, this fringe width this is linear width, right, linear distance from this center of the screen to the where fringe is formed. If angular fringe width we ask, then what is the expression for angular fringe width, right? Angular fringe width. Actually, generally questions does not come from this topic, but still you must know the formula for angular fringe width. This is the formula for linear fringe width, linear distance from the center of the screen. But suppose the first bright fringe is formed at this point, so centers, this angle is theta, this angle is theta. So this angle theta is the angular fringe width, and this angular fringe width says separation between the two bright and dark fringes are same. So we always take this angular fringe width as beta by this capital D. So beta is lambda capital D by small d. So it becomes dd cancel lambda by small d. This is the expression for angular fringe width, theta equal to lambda by small d. You just divide by capital D in fringe width, you get angular fringe width, right? Okay. Pause it and note down. Okay. One more thing is left in this one. What happens when this Young's experiment is immersed in liquid? Then is there any change in the part difference or fringe width? Now, what will happen if Young's double slit is immersed in liquid? Okay, is there any changes in the fringe width or part difference? Suppose if for air, fringe width is what? Lambda capital D by small d. This fringe width is for air. And for liquid, fringe width for liquid is what? Inside the liquid, velocity of light changes, wavelength of light also changes. So you take lambda dash capital D by small d. And one more thing, you know the relation between lambda and lambda dash. Okay, when light travels in air and when it enters inside the liquid, its wavelength changes, its velocity changes. So what is the relation between this lambda and lambda dash? Let mu be refractive index of liquid, and you know the relation between this refractive index is equal to velocity of light in air by velocity of light in medium. So you can write wavelength of light in air by wavelength of light in medium. From here you get lambda dash equal to lambda by mu. You just put this one in equation number 2. You get fringe width when experimental setup is kept inside the liquid is, in place of lambda dash you write lambda by mu, it means mu d. This is equation number 3. Again from 1 and 3, you get fringe width in air by fringe width in liquid. Just divide these two equations, you get lambda capital D by small d divided by lambda capital D by mu d. So this d to d cancel, this d cancel, lambda cancel, you take mu upward. This one is mu. It means fringe width when kept inside the liquid is what? 1 by mu naught times fringe width kept inside the air. This is the relation. So when this experimental setup is kept inside the liquid, its fringe width increases or decreases? It decreases 1 by mu fringe width of air. So you can write fringe width reduces or decreases when kept inside the liquid. Okay, pause it and note down. Okay, one more thing. Suppose when we introduce one transparent thin sheet of thickness T and refractive index mu in the path of one of the two interfering beams. Now, what effects on the path difference between the two interference beams when this transparent sheet is placed? So there is displacement of interference fringes when you placed one transparent sheet in the path of one of the two interfering beams. This T is thickness of sheet, transparent sheet, mu is refractive index of sheet. Then extra path difference introduced is this one, delta x equal to beta by lambda mu minus 1t. You just remember this formula. This is very important. Some numericals comes based on this formula. So extra path difference introduced when transparent sheet is introduced between one of the two transferring beams is delta x equal to beta by lambda mu minus 1t, where t is the thickness of the sheet and this mu is refractive index, lambda is wavelength of light used. Okay, so with this I am going to end the class. In the next video I will solve some numericals based on this interference topic. After that we will start next topic, diffraction. Till then students, keep revising and stay tuned with this channel. Bye bye. Take care.